Alright, so I want us to revisit the problem that we tackled in class today. We have 0.487 grams of quinine. Remember I mentioned earlier that quinine was one of the first successful treatments for malaria. It's isolated from the bark of a South American willow tree. And in this problem, we're also given the molar mass of quinine is 324 grams per mole. And when we combust quinine, we obtain 1.321 grams of CO2, 0.325 grams of H2O, and 0.0421 grams of N2. Now, one of the mistakes that I made in presenting this problem in class was overly complicating the amount of nitrogen. All of the nitrogen must come from the nitrogen in quinine, and when we have the mass of the nitrogen gas, since it's all nitrogen, our mass of nitrogen is given to us. It's 0.0421 grams. So I'm going to leave that as is. If we want to determine how much carbon we have, we're going to start with the fundamental fact that combustion yielded 1.321 grams of CO2. And we want to find how much of this is carbon, so we're going to multiply this by the molar mass of carbon, 12.011 grams, divided by the molar mass of CO2, which is 44.01 grams of CO2. Of course, using our dimensional analysis skills, we know that grams of CO2 cancel. And with a little simple math, we can determine that the mass of carbon in this sample is 0.360521 grams. So now we know the mass of carbon, and we also know the mass of nitrogen. Next, we want to find the mass of hydrogen. We're given that we have 0.325 grams of water from our combustion analysis, and we have 2.02 grams of hydrogen in 18.02 grams of water. Again, we get this from percent composition. And when we simplify this expression, we find that we have 0.0364 grams of hydrogen. The only thing we don't know now is the mass of oxygen. So if we take the mass of hydrogen plus the mass of carbon plus the mass of nitrogen, and we subtract that sum from 4.87 grams of quinine, we arrive at the mass of oxygen, which is 0.0480. To simplify this calculation, I'm going to convert all of my grams to milligrams so that they represent integers that are a little bit easier to deal with. So we have 360.521 milligrams of carbon. I know that there are 12 0.011 milligrams of carbon in 1 millimole of carbon. And when I simplify this expression, I get approximately 30 millimoles. We look at hydrogen. We have 36.4 milligrams of hydrogen. I know that there's 1.0079 milligrams of hydrogen in 1 millimole of hydrogen. And when I simplify this, I obtain approximately 36 millimoles. Continuing the process for nitrogen, I have 42 0.1 milligrams of nitrogen, and there are 14.0067 milligrams of nitrogen in 1 millimole of nitrogen, just like we did in class. And that gives me 3 millimoles. And finally, with oxygen, we have 48.0 milligrams of oxygen. There are 15.9994 milligrams of oxygen in 1 millimole of oxygen. And that's going to give us 3 millimoles as well. I want to divide all the numbers by the lowest number of millimoles, which is 3. And when I do this, I find that I have 10 carbons to 12 hydrogens to 1 nitrogen to 1 oxygen. This means that the empirical formula of quinine is C10H12ON, or NO. That's equal to the empirical formula. Now we need the mass of this empirical formula, and here I'm just going to go to integer values. So 10 carbons will be 12, 12 hydrogens will be 10 carbons will be 120, 12 hydrogens will be 12, 1 oxygen will be 16, 1 nitrogen will be 14. If I add all of this together, I get 162. I know the molar mass of the compound is 324. The empirical formula is equal to the molecular formula, or the molecular formula is an integer multiple of the empirical formula. So 162 times x equals 324. X is equal to 2. I multiply 2 by the empirical formula in order to determine the molecular formula. So the molecular formula is C20H24N2O2.